And just so that way I have it on here, so far we have been using capital K's, and these were thermodynamic constants, which is just a fancy term. It's an actual whole field of study. And these really are ratios. And so they will usually tell you, like, for example, how much, like what's the ratio of product to substrates at the end, or like the equilibrium constants, the KD, binding and dissociation constants, but they never tell you directly how fast. So it's limited, or one of the limits, I should say, since it doesn't give you rate directly. Okay. And so that's where we get to this whole idea that we use these little k's a lot of times. Technically, it's called little k's are kinetic rate constants, or sometimes they're referred to as proportionality constants. I hate calling them that because I don't think that way. But all right. So the first thing that we're going to do is what's called a rate law. They have rate laws. And every rate law has a rate, whatever that rate is, like a velocity. Maybe it's a rate of binding, the rate of a reaction for the chemistry step, the rate of dissociation, doesn't matter, the rate of whatever, a velocity. It will have a little k that they call the kinetic rate constant or the proportionality constant. And then it's always going to have at least one or more concentration dependence. Okay, so I'm just going to call that x here, and it could be, and it very well could be to a power. So this is just one example, but you can imagine if we have, go back to our 7th grade dance scenario, and you have a limited amount of time. The dance only goes from 7 p.m. to 9 p.m. You got the boys on one side, you got the girls on the other side. The rate and how quickly they start to dance is going to be dependent upon the concentration of two things: how many boys there are and how many girls there are, right? And so then that rate law would equal rate is equal to k times the concentration of boys times the concentration of girls. Once again, we're only assuming it's a boy-girl dance and nothing weird going on. Okay, so, but that's just an example. And so every rate law will look something like that, or maybe it would look something like another example would be rate. Let's say that we have an example where it's got the concentration of two different things, like A times B. And once again, A and B could be to a different power. For example, if it takes two A's to react with one B, it would be the rate is equal to K times A squared times B. I guess I should put like X's and Y's or something. If I was going to be, X and Y, the most legitimate. So this, once again, this is called that's the generalized rate equation. Don't be surprised if a chemistry book or something may put velocity instead of rate or V. It's the same principle here. Calculus books, I don't know how much like biology and chemistry they put in your calculus book, but they can actually use this too. We'll talk a little bit about it. I don't know if it's out today or called integrated rate laws, which actually does integration. I usually try to make it look less scary than what I do. All right. So, what are some of the possibilities? So, we can imagine, I'm going to use V just for the rate. And I'll write that out here once, just so that way I don't have to keep writing rate over and over and over again, a velocity or a rate. You can literally, and I'll show you an example of it later, but you could have what they call a zero order rate. Zero order. And what that is you'd have your, we're going to talk about, like I said, we won't see this one very often in vivo, like in a lot of literature, but it's still required to be covered up for MCAT, and it does occur once in a while. But starting next class, we're going to go over what's called first order and second order. And those are the ones that happen the most frequently. Okay? Okay, and then we're going to start using those and put them into real world examples and like, what does that mean? So I'll go ahead and in class of prayer. So dear Heavenly Father, I want to praise you and thank you for this amazing, wonderful day, Lord. We ask that you guide us and direct us, keep your hand over us, and let us know your will for our lives. In Jesus' name I pray. Amen. This is zero order. We don't see. I'll show you an example later on of when it would be biologically relevant, but it's only in certain conditions. It's not like, I can't think of anything off the top of my head that's always zero order. Okay. First order is the next one. Okay. There we go. So first order does happen a lot. And remember, this is always true. Rate, my ire against Apple stuff sometimes. Rate, which I'm going to put V, because usually that's what we're talking about, it's a velocity, but in theory it can be the rate of anything. V always has to have what? What's the one thing that every single rate order has to have? Little k. And then you always have to have it times the concentration of something. Okay, and if it's zero order, it's something to the 0 power, and that's why it cancels out. But this time, it's going to be the times the concentration of something to the power 1. So I'm just going to say A, for example. Okay? And so that's why it's called first order. The exponent on the A is 1. Okay? I don't know if I specifically pointed that out before, but the exponent in the zero order would be 0. That's why they call it zero order. Okay? All right. And so this could be just a reaction of something like A going to B, or usually you don't see this with binding so much, because usually when we're talking about binding, it's going to be dependent upon two things coming together. That actually makes sense. But you could actually make it, or there may be even times in vivo where you have so much of one of them that the concentration no longer matters for it. And so that's when they literally call it pseudo first order, because it behaves just like first order for how fast. But you can imagine, usually in vivo, you have more of the ligand and less of the enzyme or whatever it's going to bind to, less of the receptor. And so if it's pseudo first order, you have so many ligands that they're just out there, and there's, the ligand doesn't come together is totally dependent upon the concentration of the enzyme and the receptor. Okay. All right. So once again, they call that pseudo first order because it behaves like a first order, but in reality, it's two things. And if we do a review from the last time, the units for velocity is always going to be some type of concentration. Typically, we usually use molar. Sometimes they may say millimolar or micromolar, but something molar per unit time. And so I always like to say per second, but in theory, that's like the default unit is second, but some papers may do per minute or per day or per hour, something like that, per second. Okay. Now if we look at the constant, what are the units on A? What are the units here when it's in the square brackets like this? It's molar, right? That's the concentration, it's molar. So I should have done these all in different colors. So since its concentrations are already in molar, now we have to find, even though it's not as pretty, I'll say K is this color. Now we have to find the units of K. In order, since V is in molar per second and A is in molar, what are the units going to be for K? Just like in algebra, you've got to get the two sides to match up. So what will be the units there? Well, it can't just be seconds, because otherwise it'd be S times M, right? So what will the units be? How do we get a seconds on the bottom? It's 1 over second. Okay, so the units for it, remember these are just units, literally is 1 over second, or 1 over per unit time. And so the way that they say that, usually the way that we write that is S to the negative 1 power. And they'll even say a lot of times we'll say it's per second. Okay. That's me, or per minute, or per hour, per day. So that's how we get molar over seconds. you just have to, it's some constraints, but you just have to remember that it's the number there that's important. So if it was 100 per second, that may be fast. But if it was 1,000 per second, that's even faster, right? Or 1,000,000 per second would be even faster. But 0.00001 per second would be very, very slow. Okay. All right, and so just to reiterate, the rate here, whether it's binding or catalysis, whatever, the rate is only dependent upon the concentration of one thing. So for a second order, reaction, knowing what we know now, remember there's going to be V is equal to, what does every rate law have? A little k. Well, if zero order, the exponent was equal to 0, and first order, the exponent is equal to 1, what do you suppose in the second order, the exponents are going to equal up to? 2. Yes. So there's two ways to do a second order. One, I'm going to write it out here to the side. One is, you can imagine we can have A plus A. Oh, whoops, I said A plus A, that was B. A plus A, for example, either going to make B or going to make A2, where they're connecting together. For example, the binding of two things together. But it could be the binding of two the exact same thing. Or you can imagine it, another example would be like two things coming together to make something else. Okay, A plus B going to make C plus D or whatever. So in that first scenario, we have V is equal to K. Oops. But it would be equal to A, the concentration of A times the concentration of A, or A squared. So, but the exponent still equals 2. So I'll give you a moment to write down the rate law for the lower example. I had like an allergy attack or something this morning as well. I had a problem breathing. I'm trying to see if tea will help me. The person couldn't even talk. And then I sounded like Darth Vader. Kind of thing. My throat was like all swollen. I don't know what I got the hold of. So, over a year ago, well, actually, it's been a year and a half. And some of you knew, in class back in the fall of 2016, I got sick and was hospitalized. Of course, they thought I had COPD, which I don't smoke. I couldn't find out I don't. And they thought it was asthma or something. But I couldn't find out I have a disease called eosinophilic gastroenteritis. And so I have an eosinophilic immune response to different things. Some of it's food, it can be environmental. But then I swell up. But you can't take the inhaled corticosteroids like asthma. They don't work. So okay. So that's why if I sound a little more hoarse than normal or start coughing a lot, that's what it is. I don't have the flu. All right. So the second order one is V, and once again, we just keep saying it over and over and over again. Every rate law, the rate is equal to, what comes next? K. But in this instance, it's going to be, what will come next? V is equal to K times, what do we put down here for the concentration or concentrations? For this example here, it was A times A, which is A squared. So in the lower example, it would be A times B or B times A, it doesn't really matter. And each one of those is to the first power, but 1 plus 1 is 2, and that's why overall it's second order. So sometimes whenever they speak or talk about this, they'll say, for example, it's first order with respect to A, in first order with respect to B, but overall it's second order reaction. Like I said, usually a lot of the stuff that you see is more like this. Two things coming together to bind or something. Okay. And it doesn't matter which example that we choose, the units are going to be the same for K. And so what I may do, actually I'll probably do it on this bottom because I can scroll everything up. But the units are the same for both of them. Okay. So remember, V always has units of like molar per second. We're trying to find K's units. The unit for the A would be what? What is A's units right here? It's molar. And B's units would be molar. So it's molar times molar, which would be molar squared. That's why I said that you could also do it right here. Be molar squared. Okay. So then what does K have to be? How do we get only one M on top and one S on the bottom? Whoops, that's supposed to be parentheses. How do we do that? How do we cancel out an M? Right now we've got two M's on top, but we only need one M on top. You gotta put an M on the bottom. And how do we get the S on the bottom? You put it there. And that's a 1. So it'd be 1 over molar seconds. But usually we don't write it this way. Usually it's written out as M to the -1, S to the -1. And they call it per molar per second. The per means divided. You move back to yeah. But that's why for each order, and so you could, if you did it on your own, for something that's in third order overall, which they call it termolecular, which I think sounds really stupid. But termolecular, it would be per molar squared per second, because it'd be molar to the -2, seconds to the -1. The only time the S is not to the -1 is in that zero order reaction. Okay? Because then K really is molar. No, take that back. It's always still going to be molar per second. That's completely wrong that one. Completely disregard that. And so there's always going to be an S to the -1. And so, okay. But yeah, those are called rate laws. From these, you can actually do calculus and you can integrate them because they are a function. So, let's see. So, for example, when we say a velocity like miles, well, like even miles per hour, which you can use that as well, or molar per second, doesn't matter velocity, that's actually a derivative. Okay, so therefore, you can integrate, you can just do it. It's a function if you want to think of it that way from math. I would not ask you to derive these just because it would take time. And so I'm just going to give them to you and then expect you to know how to use them, okay? Because they are really important. They are listed for the MCAT. For those who haven't taken it yet in Gen Chem, I bet you do cover at least 1 or 2 of these because they are really important, both biologically and also in the natural sciences. So they're called the integrated rate laws. These are integrated. And I don't know about the calculus here, but I know whenever I took calculus 2, I think it was, 3, I don't know, they had us derive these just to show like why it was important. But, okay. So this is, I'll do the first one. It's called for the zero order. This is the problem with the Mac because being lefty, I hit the button whenever it sits down. For zero order, this is the equation. the concentration of A at any particular time, you can determine it based off of this. This is assuming it's decreasing. If it's increasing, you just don't put the negative sign. But the reason why I put that is because the reason why this is biological, does anyone know why it's biologically relevant here for the integrated rate law for zero order? There's one in particular, it's used on an everyday basis. Do we know what that is? This radioactive decay, like the decay, because it doesn't matter how much you start off with, it decays at the exact same rate. That's why they can do like, like radiocarbon dating and all that kind of stuff. And so that's why they almost always show it with a negative, because that's the one that happens. But in theory, if we had something that was increasing with zero order, you just wouldn't include the negative sign. Okay, but let's say at any time t, that's why I say in Gen Chem you'll probably do this at least once. They'll probably have this as an example. Since it's decreasing, you have to put the negative sign. It depends on how much you started off with. So A naught or A at time 0 times that K, which is the zero order rate constant, times T. Okay. Now in Gen Chem, at least whenever I taught Gen Chem, I used to give this equation, I think it was, but then I would have you solve for the T1 half. Like how long does it take for half of it to go away? This one I'm gonna give it to you because this one's not too difficult, because for at T1 half, this number right here is equal to 50% of this number right there, so that's why they cancel it out. So, what is that? Zero order, is that right? It may not be for radioactive decay. I forgot what order this one was. I may be off on my radioactive decay, so I don't have it in my notes. But the T1 half is equal to the concentration of A divided by 2. I take that back, so I think radioactive decay is first order irreversible. So you can't go backwards. All right. All right, so then we're not going to do the one for second order because it's not that important here. But for first order, there are two different types that are important for enzymology. There's one that's called first order irreversible, so it can't go backwards. Okay. And what it is it's the concentration of A at any time t. And I'm not for sure who actually sat down and figured this out, but it's equal to the concentration of A naught that you start off with times E to the negative KT power. Once again, in Gen Chem, I used to have people figure this up on their own, but I'm just going to tell you the 1/2 time, just because I want to get through it, is equal to the ln of the natural log of 2 divided by K. And if we have first order irreversible, there's also a first order reversible, so it can come on and off, come on and off, come on and off. And that's when it becomes much more difficult. So let me write it out first, and then I'll explain what it means. Concentration of A naught divided by times
times e to the negative. So please, I wouldn't even figure this one up using calculus. I would leave that to the powers that be. There we go. And then the t1 half I'm going to write down here, which is actually not nearly as difficult as the rest of it. Let me give everybody one to get caught up writing. Okay, so what this states, does anyone know what does it mean by Kf and Kr? Since this is a reversible reaction. What do we mean by Kf and Kr? So if it's reversible, what does that mean? Say that we have binding that's occurring. So you got an enzyme and a substrate, or a ligand and a receptor, or whatever. And then so it's binding. If it's reversible, it can bind and it can unbind or dissociate. And so that means you can go forward and go backwards. And so this is forward and reverse. And so what this reaction would look like would be something like this. I'm just going to say A and B, but you get the idea. Where we'd have a forward rate and a backwards rate. Okay. So that's what that means. This one is dependent. The overall amount of A that you would have at any point in time is going to be dependent on both. How much is going away and how much is coming back. Whereas if it was irreversible, it's only going away. That's why it becomes a little bit more complicated. So one thing that we can do, like let's say you have some system and you don't know, you measure it. You know, we can measure how much is bound, all that kind of stuff. So we measure that as a function of time. But you don't know what, like how do we know what kind of binding it is? Is it zero order, first order, second order? If it's zero order, it's easy because as time goes on, it doesn't matter how much you have. Okay? And so, that's not, you know, it doesn't really matter so much. But between the first orders, what you do is you can actually plot these. Okay? And you're going to get two different shapes whenever you go to plot them. Okay. So, zero order literally is a line, because it's y is equal to mx plus b. Of course, the b, you always have that plus or constant or whatever. I think calculus always put plus c for the constant. Here's plus a b in algebra. But here you see something to be exponential, and this would be even much more complicated with that. Okay, and so therefore, you'd be able to figure it out once you start to plot these. Right. Are there any questions over the rate laws and rates? For this class, most of what we're going to be talking about, whenever we start talking about little k's, we're going to be looking at the numbers, you know, like 100 versus 1,000 or whatever, and talking about things, whether they're the rate limiting step or not, or how fast or how slow they are. But it's also the units. And many times we may describe things, oh, it's zero order, first order, or maybe second order, but we wouldn't typically go into anything higher than that. Like I said, biologically, I can't think of anything off the top of my head where that would be pertinent to. Okay, but
At least in theory, you can do it. And in labs, they do that in chemistry. They do that sometimes in higher orders. They want me to do with enzymes. Oh, right. So let's start to put some of this into practice. One of the things that's stated for the MCAT, and we started on, are how do you know these sometimes they call it the reaction schemes, sometimes they call them energy diagrams. How can you tell the rate limiting steps and start to put these big K's and little K's and all this together, at least figuratively. And so this is what we're going to do. So let's say, for example, we have an enzyme plus a substrate. We're going to assume that it's reversible. It's going to bind, and remember, that's called the ES complex. Sometimes we also call them a Michaelis complex, named after a scientist who helped drive the Michaelis equation, which we'll probably be doing maybe as early as towards the end of next week, but it may be not until the beginning of the week after that, which actually would be Wednesday the week after that, because I think that's President's Day. Okay. Many enzymes will also have an EP complex. That, to my knowledge, doesn't have a special name. I've never heard it referred to anything except for the EP complex, or enzyme product complex. And then, of course, you're going to want the product to disappear, to leave. But you've got to get your enzyme back, right? So this one's fairly simple. There's only two intermediates, an ES and an EP. But there are how many steps? There are two intermediates. We have how many steps? 3. Let's not do my count. First station. 1, 2, 3 steps. And so, yes. All right. One thing that we do in enzymology, which I think I stated this like real early on, is each step has got a little K, but what they do is they call that one K1 going forward. Going backwards, it's called K minus 1. So this one would be K2 and K minus 2. This one would be K3, K minus 3. There are some of these reaction schemes and mechanisms that are really complicated. They can even get to multiple dimensions, which we'll do that a little bit by the end of the semester. Like what happens when you put an inhibitor or something like that, or what if it's got more than one substrate? But it's relatively easy to draw in 2 dimensions. There are some that go into the third. We need like one of those things like you see on TV where it shows like a hologram. That would be cool. Okay. All right, so let's draw an energy diagram. You can put, I don't usually like to write the letter E here because it gets energy and enzyme confused. So you can put free energy, it doesn't bother me. Or you can even just write out energy. Okay, free energy, what have you. Now, just given the information above, we don't know like how fast or how slow something is going, right? So I'm going to draw an example using this. Like, does it prefer to go to the left? Does it prefer overall to go to the right? Because enzymes catalyze the backwards and forward reactions the same amount. Okay? A lot of people, that's something that people often will miss. Because they'll say, oh, it only goes forwards, it makes it faster to go forwards. It also will make it faster to go backwards. And some enzymes deliberately do that, and our body utilizes that. Then some enzymes in vivo, they only go one direction. But the reason why they only go to one direction is usually because of some other reason. So for example, one of the enzymes that I worked on, even though it catalyzed both the forward and the backwards direction, in vivo it only went one way because one of the products was so tiny it left immediately. And once it's gone, it's too hard to get it to come back. So that's why in all practical purposes, it only went one direction. In vitro, you could force it to go the other way, but in vivo, it didn't do that. Okay,
So, in the beginning, we have enzyme plus substrate. And it's a relative amount of energy. I'm just saying there. I don't know why I picked there because I was led by the Spirit to do so. Okay, some of this may already go for like thinking 1 or 2. What happens? Will the energy go up or go down in order to get these to bind? It's going to go up. And you can imagine the reason why. It has to do with entropy and it's entropic in the sense that it's more, they're happier being 2 separate things. You increase the amount of randomness by having 2 separate things and forcing it together. Some, they talk about the hydration effect and solvation effect because there's water that has to form around it. In vivo, there's water that's going to form around the enzyme and the substrate. And in order for them to come together, you're going to have to disturb that water and all that kind of stuff. But yes, it's going to go up. And I don't know how far up. I'm just going to show it going up like this. That high point of the hill is called a transition state. And so they usually mark it with this little double dagger. I don't know why I put it that far up, but I did. So that was the hardest point, trying to get the enzyme and substrate together. Once you get them to bind, they're going to go down in energy. And there's a minima there. So I'm going to do this in a different color. This is the ES. It's a little bit more stable energetically than the transition state. It may or may not be more stable than the starting point. Right now, am I showing it being more stable than this or less stable than that? Less stable because it's higher in energy. But remember, overall, lower energy means that it's more stable. Okay. All right. Now we're going to try to break it apart, break the bond or whatever to make EP. Do you think you're going to have to add energy to get EP to form, or is it going to go even lower? You're going to have to add a little bit of energy. Okay. Sometimes they would call this a binding step, and this the catalytic step, or the chemistry steps. That's where the chemistry is occurring. So we have to add some energy. It may be higher, it may be lower than the last minima. I'm just going to draw it like this to make it a little bit easier to see. And once again, it too will have a transition state. And you get some energy back. And it may be higher or lower than either ES or E plus S. Okay. I'll call this one EP. Okay. And now we're wanting to quote Frozen, let it go. Sorry, my wife didn't watch that. I've never seen it. I was okay without seeing it. Okay, so what are you going to add? What do you suppose is going to happen? Are you going to have to add a little bit of energy to get the P to go, or is it just going to keep on going down? You do. You have to add a little bit more energy. Or sometimes you may have to add a lot more. But the hill will go up. So, I ride a bike, and so I like to refer to it in cycling terms. But it goes up. And wherever I put it, once again, it could be higher than the other two. It could be lower than the other two. It doesn't. Maxima. And it's also going to have a transition state. And then, presumably, overall, it's going to go down. And we get E plus P. So our product leaves. And so each of these transition states, you could also put like a transition state for 1, 2, 3. So one little rule of thumb or piece of advice is that for every step of the reaction, you're going to have a hill. Okay? So that's why in this instance, in this example here, we had to bind. So you go up the first hill, was binding. Then you had the chemistry step. And then we had the dissociation step of the product. So if there were 4 steps, we would have had 4 hills if there's 2 steps, you have 2 hills, and so on and so forth. There's only 1 step, you have 1 hill. Of course, that means it's not catalyzed. Or if we were only looking at binding, before when we were talking about binding, we were only looking at this first step, the ligand. So that's why if we would have drawn it, it would only have 1 step. Or if you were looking at like something that didn't have a chemistry step, for example, in a histamine binding to its receptor, that's literally only a binding step. So there isn't a chemistry there done on the histamine itself. And so it would only have 1 step. Okay, so going in the forward direction from substrate to product, the way that I have this drawn, what is the rate limiting step? The rate limiting step is going to be the slowest step. I haven't given you numbers for all the little k's. If I gave you the numbers, you could look at the little k's and get an idea. So, okay, look at this. We've got one that's a 0.00001, and one that's a million, and one that's a gazillion. Okay, so you can probably figure it out. But if you're only given the energy diagram, which one is going to be the rate limiting step? Going in the forward direction? How do you figure that out? Like what one's going to take the longest?
ES to EP.
Okay, and why do you say ES to EP? What was your rationale?
It also requires the most energy.
That's exactly it. Whichever hill is the biggest hill going in this direction will be the rate limiting step. It's not always the way I have this one drawn. I think it really is the ES to EP. There's the relative amounts. Yeah, I think the E trying to eyeball it. I actually should have made it a little bit more. It's not always going to be the chemistry step. Sometimes binding may be rate limiting. Sometimes it's product dissociation. But in this one, at least by eyeballing it, since I put numbers in, it probably is the ES to EP. It's always the biggest hill. Now going backwards, now we're starting at E plus P and we're going to make substrate. In this example here, what would be the rate limiting step for the backwards reaction? E plus P going to EP. That one's pretty easy. That's the biggest hill. The enzyme that I worked on, it really did look more like this, that I worked on for my PhD at least, because that's whenever I said product dissociation really essentially made it, for all intents and purposes, only go that direction, because it was too hard to get the product to come back. Okay, because the product left. It was a little tiny. One of them technically hit 2 products, but one of them was really, really tiny. It was gone, and so trying to get that little critter back would have been, in vivo would have been impossible or almost impossible. So it was just almost always going to go, in this instance, left to right, substrate to product. Okay. But there are many enzymes that really do. They're more promiscuous, or they're not that discerning between which direction to go. And so therefore, maybe all of them are about the same. Or I should say that overall maybe about the same. And so, like if I try to give an example of that one, I'm trying to draw it free-handed. That would be interesting. Let's see if I can. It would look, whoops, once again, this would be energy. Let's see. Whoops. See if you notice, I try to draw something here, and you can go ahead and put in the E, the ES, EP, EP. It may be a little bit slower going backwards, but it's not going to be a lot slower because this hill is a little bit bigger than that. But once again, you kind of see where you're going both directions. This enzyme could easily go both directions. So, in your body, an example of the second one versus the first one, for those who are currently in biochemistry, hexokinase would be something like the very first one that we had from glycolysis, because it's a rate limiting step for glycolysis. It goes one direction, that's it. Okay. Whereas one of the reversible ones, that's what I like one of the reversible ones, like aldolase or something, it goes frontwards and backwards. Okay. And so that's also in glycolysis. And so it's one of the steps of glycolysis. All right. And let's just do one more for practice. I'll leave you with one more.
And so what I want you to do between now and Monday is on this one, I want you to draw the energy diagram, or a proposed energy diagram, where substrate binding is the rate limiting step. Because what we're going to do on Monday is pick up with this, do this example, and then start tying the little case to the big case. Because overall, when we started doing the binding of the big case, I told you, remember, it was the overall reaction, like the amount of substrate the product was equilibrium. Right? How much product you had in the end, and how much substrate you had in the end. And so we're going to be able to relate some of those to these little Ks. So how does the little Ks and the big Ks all come in together? Okay. Are there any questions?